Okay, so again, the big question we need to answer before we jump into the homework questions is where do these coordinates on the unit circle come from? Okay, because we haven't answered that yet. And so again, the unit circle, we talked about the degrees, so hopefully we know where those come from. We talked about the radians, right? 2 pi is a full rotation. We talked about that. And we even talked too about some of these coordinates, right? So let's answer this real quick. So like these points right here, and kids who are away at Disney, you might not have seen this, unless you watched my video, of course. Like we said, you were doing as you took a break from all your fun activities, watching math videos. Where did like so we like 1 comma 0, 0 comma 1, etc. Like how is it that we know for sure that like that's the coordinate? Like what makes it so it is like 1 comma 0, 0 comma 1? Like specifically about the circle. Anybody remember this? We said this circle specifically, like just thinking of this as like a whole circle, specifically like what would be this circle's radius? 1, right? And we kind of said that's all like almost like our default radius for circles because a lot of the time they don't specify it. But that is true of my unit circle. This is a circle with a radius of 1, okay? And if you think about this, right, like, so what would that mean on a graph, right? Because that's what this is too. The unit circle is like, it doesn't look like it's on like a coordinate plane, but it kind of is, right? Because each of these points have coordinates. Um, but yeah, like, so if this was 1 comma 0, that would mean it's this point right here would be 1 space away to the right from the middle, 0 comma 0, right? And so it would make sense that if it's 1 unit away, one radius of 1, and that's kind of how it is all around the circle, okay? Like all of these points straight across or up and down are exactly 1 unit away, and that's where we get these coordinates from, okay? Um, and all these other like more diagonal lines, the radius is also 1. Like so the length is kind of broken up by the different things, but like the length of this right here from the origin to there would also be 1, okay? But the only trouble is that like because it's kind of diagonal, it's a little bit harder to calculate where the coordinates of those points are. And so we have them there. Those are the values for that. But again, what I'll do here is just a little bit just like where do those come from? How do we know that those are the coordinates? And then again, we'll use this in the homework. Okay. And so you see here, there's 2 of the more common right triangles that we see. This is a 45, 45, 90 triangle. And I'm not going to, and just named by the angles inside. And this would be 30, 60, 90. Okay, again, named by the angles inside. Okay, so I'm even just going to, let me just cover this up. This doesn't exactly match up with what's on my unit circle though, because you see, like if I was even to like draw this like we would see it on a graph, right? We talked about how like a triangle on the graph, right? How we did it before. We kind of have our point up here. We kind of have our hypotenuse coming down like this. And our angle that's formed is like this, and that this side drops down. There's my right angle, okay? But what you notice too is, like I said, the big difference between this and the ones we see on the unit circle is this has a radius or a hypotenuse of 2, whereas on the unit circle it has a radius of 1. So that's what we're going to do. It's still going to be proportionate to this one. It's just let's just like cut all these numbers in half. So 2 cut in half is 1. 1 cut in half is 1/2. Square root of 3 cut in half is square root of 3 over 2, right? But again, the big thing would be, so this would be like still a 30, 60, 90 triangle, right? It's just now the hypotenuse is 1. This is this side and this is this side. Now the big connection to make, again, because what we're trying to figure out is these x and y coordinates of these points. What's the relationship between these coordinates of these points and the sides of my triangle? Yeah, you guys remember this? It's kind of like however far this is from the middle would be my x coordinate. So like this would be 1/2, okay? And then however tall this is, right? That's kind of where it would be on my y-axis, and that would be square root of 3 over 2. And so that's like, and so if you go to your unit circle too, if you look back at that real quick, you look at your 60-degree angle, what are the coordinates of your 60-degree angle? 1/2 square root of 3 over 2, okay? And so that's kind of the basis for most of these angles, okay? Is that they pertain to kind of the ratio of the side lengths of a 30, 60, 90 triangle. Okay. Most of these angles are either like multiples of 30, like 30, 60, 90, 120. The only ones that don't fit in with that are the 45-degree ones. But look at how many similarities there are between these. Square root of 3 over 2, 1/2. 1/2 square root of 3 over 2. Negative 1/2. Like, and it just, so many of these, like over half of these angles, actually exactly half of these angles, have those as their coordinates, right? A variation of square root of 3 over 2 and 1/2. Okay. Because so many of these are just a bunch of 30, 60, 90 triangles just kind of turned in different directions. Okay. So that's where all those come from. Okay. And I'm not going to go into as much detail, but you could say something similarly with a 45, 45, 90 triangle, right? So 45, 45, 90 triangle with a hypotenuse of 1 would also have side lengths. And we said this too about a 45, 45, 90 triangle, that the side lengths are going to be the same when, because the angles inside are the same too. So you notice for all the 45-degree increments here, square root of 2, square root of 2, both of those over 2. And then it's the same, just, and you notice too, the only other thing that changes too is when it's in a different quadrant, like in quadrant 2, the x value is negative. In quadrant 3, both of them are negative, and etc. Okay. So that's just, again, and that still might be confusing, but that's just a little explanation of like why these coordinates are the way they are. Is just, now the other extra thing with this is, so like if I asked you, what's the sine of that 60-degree angle? You guys remember this? We kids who were at Disney, you probably were even still here for this. If I asked you to find the sine of this 60-degree angle, what does that mean? Like if we're thinking from this perspective of a 60-degree angle, like what do I, well, you guys know this. What do I do? Right on the board, opposite over hypotenuse, right? So think about from the 60-degree angle, my opposite end of that would be square root of 3 over 2. My hypotenuse is 1. Okay. So with that, and then just think about this too. Anything over 1 is just itself, right? So we could say sine of 60 equals square root of 3 over 2. Okay. Now, here's the connection to make. This is the big deal, and this kind of bringing it all together so we can do this homework assignment. Is look at my coordinates of my point for this triangle, okay? And then look at my answer for sine. Okay, look at this. This is going to be true for every single angle that we do. The sine of the angle is equal to the y coordinate, okay? And so that's huge, okay? So that, and you'll see that, that's actually printed on your packets here on the very bottom of your unit circle, right here. So you'll be given this on the test. But that's what this means, is that finding the sine of any angle on your unit circle is just equal to that y coordinate. And the same thing happens for cosine too. You think about cosine of a 60-degree angle, right? It's the same thing, except it's just the adjacent over the hypotenuse, right? So if it would be, for cosine, it would be 1/2 over 1. And again, 1/2 over 1 would just be 1/2, right? And so what's 1/2? 1/2 is my, a different color for that, x coordinate, right? And so that's the same thing with cosine. Cosine of any angle on your unit circle would just be the x coordinate of that point. And again, and that really only works because my hypotenuse is 1, right? So anything over 1 is just itself. Yeah, when we look at the unit circle, the hypotenuse or the radius is always 1. So that's why it works. Okay. Then just one last one to go over here. We got to talk about tangent, and then we'll be good to start the homework. Okay. So for tangent, there's no shortcut like that for tangent. So if I said, like, what's the tangent of 60, it's still going to be the y value over the x value. And we talked about that over here, right? That's the same as we've been doing. It's just, we have to tangent's the ratio of y over x. And you also see on your packet here too, is printed as, you could think of it also as the value of value of sine over the value of cosine. Kind of the same idea. So like I said, keep that unit circle out because we'll definitely need it. And then have that homework out too. Okay. And I'm not going to do every single one, but let's just talk through some of these because again, you'll see these are quick, like max like 30 seconds on some of these. Okay. So again, cosine of 225. Just unit circle, 225-degree angle, so find it. It's down here in quadrant 3, right? And so for cosine, what coordinate am I looking at? Well, actually, for this angle, it's nice because they're actually both the same. But I would look at x coordinate for cosine, right? And that's just right below the unit circle if you forget. Cosine x, sine is y. So my answer is just the x coordinate of that 225-degree angle, negative square root of 2 over 2. Now, let's doing a tangent one again, because there's one other thing to talk about with tangent. So again, tangent of 210. So again, same idea though. You look at your unit circle. You look for 210 degrees. Okay. So 210. Again, but it's not just one of these fractions. It's kind of y over x. Okay. But here's the deal. And again, you see this down here. Tangent is just y over x. Okay. Here's the deal. And I'm going to write this. You can write this right on your unit circle page there on your review. What we do with tangent, if I could spell, that's not how you spell ignore. Ignore the denominators. Okay, and I'll explain what that means here. We ignore the denominators because look at all these coordinates. If we thought about y over x, basically all of these are fractions, right? And so if we thought about like the y coordinate over the x coordinate, that'd be like fractions within fractions. It'd be a big mess, okay? But look at all the denominators of every single one of these fractions is 2, right? And so if you don't have to write this, but just think about like 1/2 over 1/2. So, well, something over itself is just equal to 1, but like that would be equivalent to 1 over 1, which is just 1, right? So like when we deal with this sort of thing, like almost like everything being over 2 kind of like cancels itself out almost. So basically what we could say for tangent, it would be the numerator of the y value over the numerator of the x value, because we're ignoring the denominators. Those aren't going to come into play and affect us at all. Okay. So that's the deal with tangent when we do these from the unit circle, okay? So again, going back to that, so tangent of 210, just the numerators, so it would be -1 over square root of -3, or negative, and again, negative over negative is a positive, so we could change that to 1 over square root of 3, and again, if you wanted to rationalize, you could say square root of 3 over 3, but, and then 64, so secant of 240, so secant, we're dealing with one of our uncommon inverse trig functions, right? Those other 3. And so what we have to think here, it's still going to be the same process, okay? Just we have to think, what is the secant the inverse of? Like what original trig function does that connect with? Cosine, right? And so we want to kind of do the same process with cosine. We're just going to do something at the end. Okay, so we go to 240, we go to cosine. The x value for this point would be -1/2. And so what do you think we do? If it's secant, what do we do when we go from cosine to secant? It's the reciprocal, right? So we just flip it, okay? So instead of being -1 over 2, it's just going to be -2 over 1. So again, connects with cosine. So -2 over 1 or just -2, okay? So when you're dealing with an inverse trig function, you just do the same way with the original and just flip it at the end. But tangent of 420 degrees. Okay, so now what's the issue? 420 degrees. If you looked for that on your unit circle, you would have no luck because that is too big, right? Our unit circle only goes up to 360. So what do we do? 360, right? So 420 minus 360. Okay, because what we're doing with that is we're kind of taking away that one full rotation it would have made. So 420 minus 360 would be just 60, right? So we know that the tangent of 420 is going to be the equivalent of tangent of 60, and then I'll be able to use that 60-degree angle to find my answer there, okay? Yeah, 67 through 70, just look for the number of radians on a unit circle, same type of thing, okay? Now for 71, you notice with this one, again, how you know a number of radians is going to be on a unit circle or not, obviously kind of look for it around the circle. But like if it's less than 2 pi, right? 2 pi equivalent to 360 degrees, one full rotation. So like 7 pi over 4 is on there, right? Because 7 divided by 4 is less than 2. But 9 divided by 4 would be 2.25, more than 2 full rotations, which means we're kind of in the same situation as we were for like 65, where It's too big. That accounts for, it's like one full rotation plus a little bit extra. Okay. So again, we would need to kind of go coterminal and think like, okay, I need to kind of take away one full rotation to find what the what the equivalent coterminal angle would be, and so I can use those coordinates. Okay. So for 9 pi over 4, and again, just as we're dealing with radians, just a reminder, you can always convert these to degrees, multiply by 180 over pi. Okay, if you don't like dealing with all this fraction business. So yeah, to subtract though, for subtracting 2 pi, again, this is a fraction, so we need to think like, okay, if I'm subtracting a fraction minus something else, I would want it to have a common denominator. So I think 8 pi over 4 would be equivalent to 2 pi. And so now I can subtract 9 pi over 4 minus 8 pi over 4 equals 1 pi over 4. And yeah, you will be able to find pi over 4 on your unit circle. And then you kind of go through the same process for that. Okay. So that is for 71. And then 72 is pretty similar, and there's actually 2 full rotations for that one that you can, so you can kind of subtract 2 pi twice or subtract 4 pi. Just last one to show you, then again, we'll pick up with 77 and on tomorrow. With a negative, what am I going to do here to get this to be, because negatives aren't on your unit circle either, what am I going to do here to bring this to like, so I can refer to a coterminal angle that is on my unit circle? So it's just, if it's over 360, you subtract 360. If it's below that, if it's below 0 into the negatives, you add 360. So this would be 73 sine of 120. So 120 degree angle is equivalent to a 240 degree angle, or negative 240. And you can kind of go from there. And then same, like last one, same with 75. Negative 1 pi over 4, too small, into the negatives. So we can add 2 pi to that, or again, adding 2 pi. You need a common denominator to add too. So this would be negative 1 pi plus 8 pi would give you 7 pi over 4. So 75 would be tangent of 7 pi over 4. And then you can look on that angle for your tangent, okay?